Welcome back to my solving of Advent of Code 2022. This is day 8. Let's get started. The expedition comes across a peculiar patch of tall trees, all planted carefully in a grid. The elves explain that a previous expedition planted those trees in a reforestation effort. Now they're curious if this would be a good location for a treehouse. First, determine whether there is enough tree cover here to keep a treehouse hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter to generate a map with the height of each tree or puzzle input. For example, this. Each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. The tree is visible if all of the trees between it and the edge of the grid are shorter than it. Okay? Only consider trees in the same row or column. That is, you only look up, down, left, right from any given tree. All the trees around the edge of the grid are visible since they are already on the edge, and there are no trees to block this view. In this example, this only leaves interior 9 trees to consider. So, let's just take a look, right? So this 5 is visible from both top and left. So this 5 is visible from top. This 1, however, is not visible. So that is not visible because there's a 5, there's a 3, there's a 2, there's a 7. Okay. All the trees around the edge, yeah, so 5 is visible, 5 is visible, 1 is not visible. All right. With 16 trees visible on the edge, another 5 visible on the interior, total of 21 trees are visible. How many trees are visible? Okay, let's grab the input. It's a nice wide grid. How long is this thing? 99 lines, so it's 99 by 99. So pretty big. Well, let's start by just reading in the data. So for this, we want a matrix of integers. So a grid is a list of int, and we're going to call this a grid. And it's going to be int I, in for in line. So each line, just go through each character and cast it to an integer, and that makes this a grid. Okay, so that should read in the input fine. We can even just test it real quick. Whoops, that's old Python syntax. Print the len of the grid. cd day8 Python. Well, that was loud. Day8 example. All right, grid is not defined. Input.grid, input.grid. Okay, 5, and then if we do the input, we get 99. All right, cool. So we are working, so now we have to figure out how to solve this, right? So what's the naive approach? The naive approach is, first of all, we can, as the example does, we can ignore all the outer trees as they're all visible. So we just know they're visible. So we only need to consider the inner grid. So in this case, it's 3 by 3, but in our example, it's like 97 by 97. So still pretty big. So then we go through each integer, and we can grab everything above it, everything below it, everything to the left, and everything to the right. And we simply walk each line to see if there's a number greater than it. And if any one of those lines above, up, down, left, right, have a number that's, oh, my light isn't on. Turn that on. Now it's brighter. If any one of those grids have a line that where all the numbers are less than the value there, then it's visible. So we can just say, so is there another smarter way to do it? So how long, well, I guess the question is how long will that take, right? So if n is the length of a side, right? So n97 or 3, right? So we are going to go over the 3 by 3, so it's n squared. And then for each one of those, we're going to walk n right and left and n up and down. So it's 2n, but in big O notation, you just call that n. And then, so that will be, and then we're going to do comparisons, a bunch of comparisons to one number. So that's O of 1. So it's going to be O of n cubed. So, you know, with our input being 100, 100 times 100 cubed is what? 100,000 operations. That should be doable in a short period of time. Very doable. It's not optimal, I'm sure, but it's very doable. So I'm just suggesting in order for speed, we should just go ahead and make the naive solution. We can think really quick if there's a smarter way to do it. You could definitely do like a marking system where you like start from the outside and you mark things as less, but I still think that might be maybe n squared log n, right? But we're just not saving that much time by doing something fancy like that. I think the best improvement we can make is, you know, instead of walking each number, we can just do this generic comparison. Yeah, I think we should just go for the naive solution. I think it'll be fast enough. So let us go. So let's make a function that can tell if a single number is visible. So is visible. We'll do grid is grid and location. We're going to define a location thing. Location. Just call it a loc. That's a tuple of int. So it's and it's going to return a bool. Okay. All right. So ij equals loc. So I is going to be our row, our grid first index, and j our second index. So so first we want to grab everything to the left. So left of this location is going to be grid of I, and then we're gonna do j, we're gonna do everything up to j, right? But not including j. So that should be good. And then right is grid I, and it's j plus 1. So these are slices, so we're getting all the values. So in this case, like right would get 512, left would be 2. And this actually works for edges as well. Up is going to be row j. So we're going to have to do a little list comprehension for row in grid less than I, because it's sort of 0, 0. So the first value is this row. So, and then down is, it doesn't really matter but what we call these, but for row in grid, and same thing, I plus 1 colon. Okay, so now we have all these collections, and we just need to see if any one of them have all their numbers less than our value. So we want to do value equals grid ij. I think there is a nice matrix math. I think if we had NumPy, you could do ij. We'll just do this. All right. So what I'm going to do is actually do the least. I'm going to start with the least number of these left, right, up, down. So our lines equals left, right, up, down. Lines.sort key equals lambda line len line. So now we're going to sort it by how many values are in the line. So for 5, this is going to do this 0 and this 2. And this is just going to be a little bit more optimal for some of these that are near the edge. sorting 4 values is very cheap. So I think it'll be just a tiny bit faster, just a little improvement. But you would really have to test it. I'm not sure if that's true. And then for line in lines, if every, is that a function? Python every all. The all function. Is that what it's called? All returns true if all elements of the given interval are true. Yeah, that's what we want. All right, so it's the all function. So if all elements in, so what it was if all are true. Okay, all right. So then we just put an interval in here. If all elements are less than the value. So v is less than value for v in line, return true, then it's visible. And otherwise, if all lines return false, return false. All right, so this solution should be n cubed, but I still think it'll run pretty fast. So we're going to implement it. So for we want a function that'll give us all elements in the grid. So def all indices for I in range grid len grid, for j in range len grid I all right, sorry, I'm spazzing out here. So I really actually want to return an interval, so yield ij. I don't know, I guess, is iterable a iterable? Is that a type? Hopefully it's a type. All right, it's actually a generator. Maybe there's a generator type. Generator. Cool, it's not yelling at me, so there's a generator type. All right, so now we can just easily do for, so count equals, actually we'll just return it. We'll just do a single statement. Return sum of 1 if is visible grid input.grid location else 0 for location in input.grid.all locations. And I know I called it something else, so I'm going to go rename it. Sometimes I change my mind while I write my code. Okay, cool. So this should be ready to go. Let's do it on the example. Too few parameters for typing generator. Oh, well, I'm just not going to type it right now. List has no attribute, all locations. So we just do, that was actually on the grid. Well, we'll change it around. It's missing a self parameter. Grid is not defined. Self. Sometimes I forget Python class semantics. All right, 21. That's the answer in our case, so it works. We didn't even have to special case the edges. And yeah, it runs quite quickly, although there was a slight delay, so it did take a little bit of time, but we got the right answer. So let's continue to part 2. Content with the amount of tree cover available. The elves just need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left, right from the tree and stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. If a tree is right on the edge, at least one of its viewing distances will be 0. I just don't care about distant trees taller than those found by the rules above. The proposed treehouse has large eaves to keep it dry, so they wouldn't be able to see higher than the treehouse anyway. The example, consider the... Okay, wait. Sorry, I didn't get this. Measure the viewing distance from a given tree. Stop if you reach an edge or at the first tree that is the same height or taller. Okay, so in this case, we want to consider each tree and look iteratively at one tree farther in every direction and see if there's anything that is at least as high or an edge. So on the edges, we just get 0, but I guess consider this middle 5. This middle 5 would be 1 because the 5 is next to it, right? Looking left, its view is blocked immediately. It can only see one tree. Looking right, it can see... Okay, a tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. Okay, so you walk them individually. It's found by 4. However, you can do even better. Consider the tree of height 5 in the middle in the 4th row. So what is the highest scenic score possible for any tree? Okay, all right. Interesting. All right, we can do this naively and still be fast. So I'm going to suggest we do that, although I do think you could improve a solution by only starting in the center and moving outward. Maybe we'll do that. So let's start our part 2 solution with the scenic score of given a grid and a location. We'll return an int. So, and we just go left, right. So let's just grab this code from up here and grab the lines here. Maybe we'll copy this into some example code later. We don't need to sort them in this case because we have to consider all of them anyway. So, and then we run a return. So I guess scores equals the sum of, I guess let's make a helper function. So def scenic line score, and it's we get a value for the height of the tree, height in question, and the line of trees off of it. And we want to, these have to be sorted so they start closest to the tree. So we'll have to do that here. So don't let me forget. But if given a line sorted closest to the tree, then we just need to do count equals 0 for other height in line if other height is greater than or equal to height, just return count, and we want to do count plus equals 1 every time we get another tree, and then and if you get to the end, return count. So this is nice and easy, and we can actually just do a break here to get out of this for loop, and so we only have a single return statement. It makes it easier to understand. So now we need, so now we need to sort these. The only ones that are sorted right are the right and the down because they start at the tree in question, say this 5, and move outward. So we just need to reverse these, and we can do this with a -1 on this last index, and our up we can do also with a -1 on the last index, and that will actually, I don't want to think about how to sort it with that index. So we're just gonna do a : -1 to just do an immediate reverse sort at the end without considering how to do it in line. That might create a bug, I'm not entirely sure. All right, so our scores are scenic line score given our value and the line for line in lines, and return reduce score lambda total score total times score scores. What is the Python reduce syntax real quick? I would really like to get the actual functools.reduce function iterable initializer. Function iterable initializer, and I guess we have to do from functools import reduce. Okay. That should be good. Okay, so then we just need to get the maximum value, right? The highest scenic score. So we just want to do max star 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 scenic score input.grid look for look in input.all locations return. All right, it's not optimal, but I think it'll run to 8. Is that 8? 8. Okay, 8 is correct. And yep, runs pretty quickly. You get this 20,000 number, and that is correct. Nicely done. So yeah, we took some naive solutions here. I think there might be some smarter ways to do it, but we were careful to do, ordering on the scenic score. We really implemented some of these just very directly, which I liked, and we didn't have a large bug bite us in the butt like we did yesterday. So overall, kind of like it. I think I might reorganize some of this if I was doing it again, like kind of make a grid data class with the all locations on that. But yeah, overall, pretty good, pretty quick, pretty direct. Makes for a good episode. So yeah, that was day 8. Like and subscribe. I'll see you guys tomorrow. Peace.